Hi everyone, this lecture will cover chapters 12 and 13, focusing on understanding research results. As you have seen from the syllabus, we are not covering chapters in order of the textbook, but rather in order of importance for this class. And it's helpful to have a brief reminder of stats before we jump further into anything. Stats help us understand data collected in research by describing the data and allowing us to make inferences and draw conclusions about a population based on the sample studied. We won't be calculating any stats by hand in this class, but we will be using JASP, a statistical software. And Appendix C of the textbook has more information about the different statistical tests if you need a refresher, as it is required, and this is a gentle reminder, that stats is a prerequisite to this course. We are moving the section up to the beginning of the semester because understanding how you can analyze the data is an important early step in choosing how to set up your research study. It helps you to pinpoint what kind of question to ask. For instance, maybe you are interested in stress on student well-being. If your question is, how does stress affect students? That's not really a quantitative research question. Rather, it's more qualitative and might be answered with an interview of students, but it's not really appropriate for this class specifically. Instead, you might ask, does perceived stress affect perceived happiness? And maybe is this relation stronger in senior than freshman students? That's more of a question that can be tested statistically. For this study, it's required that you use simple analyses. So you can use correlations, t-tests, ANOVA, maybe a two-factor ANOVA or a chi-square, but nothing more complicated than that. Really keep it simple for the project you're working on. Going in the scales of measurement, we have nominal, ordinal, interval, and ratio scales. Nominal scales refer to two or more categories that have no quantitative or numerical properties. So these are all categorical variables. Think about grouping people by eye color, hair color, gender, college major, anything that's more descriptive. Ordinal scales refer to a scale of measurement in which the measurement categories form a rank order along a continuum, meaning that it cannot be quantified. So if you go to a 5-star restaurant, you know that it's ranked higher than a 1 or 2-star restaurant, which is gross, but you can't quantify an amount of distance between them. Or say if you're running in a race, you know that the person who came in first arrived before the people that came in second or third, but you don't necessarily know how much time was between them just based off of the place that they ranked. Interval scales refer to a scale of measurement in which the intervals between numbers on the scale are all equal in size, but there's an arbitrary 0 point, and that last piece is important. Temperature is a great example of this. Regardless of if you're using Fahrenheit or Celsius, you have a scale which tells you exactly how hot or cold something is. But 0 doesn't mean 0 temperature. IQ is another example of this. It's just a point on the scale, but 0 doesn't mean that nothing exists in an individual's mind. And lastly, ratio scales refer to a scale of measurements with an absolute 0 points, which indicates an absence of the variable being measured. So if you think about how fast a car is going, a speed of 0 indicates that it's not going anywhere. Length, weight, time are all examples of this. And having a non-arbitrary 0 point allows for ratios of the numbers to be formed. You can know that 100 pounds is twice as much as 50 because you know what 0 is. This really distinguishes ratio from interval scales because you cannot do this with an interval scale. 50 degrees is not twice as hot as 25 degrees when the 0 is essentially in a random place, making it arbitrary. So why is this important? Well, the conclusions we make about the meaning of a score depend on what type of scale was used when measuring that variable. Interval and ratio scales allow us to make quantitative distinctions, which are important for this class. Most of our inferential statistics, which are those that let us infer things, require a ratio or interval scale. We cannot find the average of a variable on the nominal or ordinal scale, but we can with an interval or ratio scale. So how can you describe your results once you obtain them? First, we can compare percentages. This is how we would look at a study with nominal variables. If we want to categorize people based on whether there's a difference with a breakdown of eye color between males and females, we would have two nominal variables, gender and eye color. If we took 100 males and 100 females and counted how many of each have each eye color, we could then look at the percent of each eye color for males and females and compare, likely using a chi-square test for independence. The second way we can do this is by correlating individual scores, but we can only do this through interval or ratio data. There are some more advanced techniques for looking at correlations with nominal variables, such as point by serial correlation or rank order correlations, but again, those are more advanced and are outside of the scope of this course. And lastly, we can compare group means, which is the basis of a lot of research. This could be comparing two types of people with a treatment. It could be those that get treatment compared to those that don't. Or maybe people get tested before and after treatment. And as you might guess, this requires interval or ratio data to calculate. How else can we visually describe our data? One way is with a frequency distribution, which is an arrangement of a set of scores that indicate the number of times each score is obtained. It also tends to include a percentage for that score as well. These can be very helpful for getting an idea of the data distribution. For example, I like to use them for grades and seeing how many people earn an A, a B, and so on. One way we can graph a frequency distribution is by using a pie chart, which is what you see on the screen here, in which frequencies or percentages are represented as slices of a pie. We can also use bar graphs, which represent frequencies or percentages of each score or a group of scores. So, for example, if we try to look at children's favorite colors, on the y-axis we have how many children, and on the x-axis we have color. And you can see that they're grouped by red, blue, green, yellow, and then pink. And what's important to note here is that when you're making a bar graph, the bars do not touch each other unless they are being grouped together. So for example, if we're looking at flavor preferences by gender, again on the y-axis we have how many people. On the x-axis we have flavor, the chocolate, the strawberry, and vanilla. And then we have them grouped by male or female, where females are in the pink and males are in the blue. And because they're being grouped together, the bars touch in this case. That is an important distinction when you go to make your graphs for your study. There's also what we call stacked bar graphs for when you have a lot of variables. So instead of having a big list of variables with bars that are all touching each other in multiple clumps, you would have something like this, where you have on the y-axis, in this case, it's revenue or how much money. And then on the x-axis, you have different categories. So accessories, camcorders, computers, and so on. And how this is broken up is by year. So you can see that accessories during the year 2013, that's blue, they sold less accessories or made less revenue than they did in the year 2018. And so you get some of these comparisons with these percentages within this type of chart. Then we have histograms, which look like bar graphs but have two major distinctions. First is that histograms are used for continuous data, and second, because it is continuous, the bars touch. So in this example, we have frequency on the y-axis and item price on the x-axis. And you can see that it ranges in price from $1 all the way up to $50. And because this is continuous, it's essentially one variable here just broken up, the bars are all touching. And so this is very different than categorical data, such as someone's favorite color, in which red and green and blue are very distinct and separate categories. We also have what we call frequency polygons, where we have the frequency of each score plotted on that vertical y-axis with the points connected by straight lines. So instead of having separate pieces of a pie or a bar graph or a histogram where you can kind of see those individual pieces, this is showing you kind of an overall picture to show you a general trend of the data. And so the example here is a distribution of exam scores with frequency on the y-axis, so how many students, and then exam score on the x-axis. And you can see that it's a relatively even distribution. You have a somewhat decent bell curve here, and you can see how students do on the exam overall. And because all of this is very connected, right? It's all one exam score. You can see that it has to be done with continuous data. This wouldn't work with using that example again of favorite color, in which some people like red and blue and green. If they're not connected to each other, you don't get the context or really the overview of what the data is telling you. Lastly, we have scatter plots, which are graphic representations of each individual scores. So instead of averages or percentages, you can see where each person scored themselves. This is really great for correlations, so we can see how related two variables are. Do scores tend to increase together? Does one variable tend to increase while the other decreases? In this example, we can see individuals' weight and heights and get a sense that as height increases, weight tends to increase as well. Sometimes there's also a line that goes through the graph called a regression line, which shows us how close to a perfect correlation the data is. So overall, these visual representations help us see the data. It helps us identify trends and changes and understand what is happening more so than just reading numbers. For your study, you will also need to describe your data, not just visually, but with statistics. Descriptive statistics do just that. They describe the results of the study and include measures of central tendency, variability, and correlation. Let's start with central tendency, which is a single number of value that describes the typical or central score among a set of scores. Essentially, we're trying to find one number that describes the data. Starting with the mean, which we will use as a capitalized italicized M, is calculated by summing scores and then dividing the total number of scores. We also call this the average, and while the mean is the most common, there's a problem in that it's skewed by extreme scores, and we'll see an example of that in just a minute. The median is the middle score in a distribution of scores that divides the distribution in half, so 50% above and 50% below. There's a benefit to the median in that it's not skewed by extreme scores, but it doesn't really show us the overall distribution of scores. The mode is the most frequent score in a distribution of scores, and it's especially useful with nominal data. For instance, if we're interested in how many people have green eyes or how many people have the favorite color red, the mode tells us this information. So let's talk about why mean might not always be the best measure using the feudal village example. In this village, there are 51 families. You can see that the N is 51. 50 of those families only earn $100 per year, but one family earns $100,000 per year. Together, that is $105,000 per year. If you take the mean, where you take that total income and divide it by the number of scores, in this case 51, the average is $2,059 per year, which is not very representative of the amount of money people actually earn in that village, right? The majority only earn $100 per year. So when we look at the median, which is 100, and the mode, which is also 100, it tells us more about what's going on in that village. In addition to central tendency, variability is also important because it tells us more about what's going on in our dataset. And it's defined as the amount of dispersion of scores about some central value. We have a couple of different ways of representing this. First is variance, which is indicated by a lowercase italicized s squared, which is a measure of variability of scores about a mean. And we calculate it by looking at the mean of the sum of squared deviations of scores from the group mean. Next is standard deviation, which is a lowercase italicized s in statistics, or a capitalized SD in APA writing when you're going to write your paper. This is the square root of the variance, and you can look at it as the average deviation of scores from the mean. Correlation is also used as a descriptive tool, and it's an index of how strongly two variables are related to each other. The official name of what most of us just call a correlation is the Pearson product moment correlation coefficient. So this is a type of correlation used with interval and ratio scale data. You cannot use this with nominal or ordinal scales. The Pearson correlation coefficient provides information on the strength and the direction of the relation, and it's indicated using a lowercase italicized r. The strength of the relation ranges from +1 to -1 and is weaker as it approaches 0. Please know that you can only have numbers within this range, and that if you get a number outside of this range, something is wrong. It's always between negative and +1, and the ones in either direction are a perfect correlation, in which as one variable changes, the other changes in the exact same way. A correlation of 0 means that there is no relation between variables. The direction matters here. If there's a positive correlation, variables are changing in the same direction. As one variable increases, the other variable increases as well. As one variable decreases, the other variable decreases as well. A negative correlation means that variables move in opposite directions. So as one variable increases, the other decreases, and vice versa. Just giving you some examples of different correlations. In the upper left-hand corner, graph A shows data falling in a straight line. You can see that as x increases, y decreases in a perfect manner, making this a perfect -1 correlation. Moving to graph B, you can see that there really isn't a pattern here. These variables don't really seem to be related. So we can see that there's probably a correlation of 0 or maybe just above 0. Looking at graph C, you can see that there is a trend in which these variables increase together, but it's not a perfect line. If I add a regression line through here, you can see that there is some variation from what would be considered perfect. And this correlation, if I had to guess, would be around 0.7, 0.8 or so. And then lastly, we have graph D, in which there is a general negative trend, but it's weak, right? There's even more variability here than in graph C. There is a trend, but it's closer to 0. So we are always looking at the strength and the direction of the correlation. There's also things we need to be aware of when it comes to evaluating correlations. The first being a restriction of range, where we either don't have enough data or we don't have a full range of data in our data set. Take this example, for instance. If we collected data and we only have a few participants and therefore only see this side of the graph, it would look like there's no relation, right? The data in that circle are all clustered together. Imagine this is a graph looking at IQ and only college graduates are measured. And college graduates might have higher IQs and might not vary much from each other. And if we don't include everyone from all walks of life, we are missing out on the entire data sets in which there is a positive relation overall. We also have to worry about outliers where one or more data points are outside of the general trend of the correlation, and then because of that, they skew the data. So let me give you a quick example of this. In graph A, you can see that there really isn't a correlation here. It's slightly negative, but probably not statistically significant. And the scores of each person are around the same when we look at the data itself. But say we add one more person to our data set and they score way higher than anyone else. So when we go to graph it, not only does it look like it's a positive correlation now, but the correlation coefficient itself is significantly stronger. It's suddenly a 0.085, even though that's not representative of the data. So what do we do? Well, we might choose to throw out this data points. We could do this carefully with statistics to see if it is indeed an outlier. But ideally, we would collect more data. So instead of having 6 participants, let's have 20 participants. And maybe that will fill in this empty space between the outlier and the rest of the data, which gives us a bigger picture. Or maybe we'll find that everyone else does tend to score down here, and it helps us to confirm that this indeed is an outlier. We also have to watch out for curvilinear relationships. The Pearson correlation test looks at linear relations, meaning that the variables fall in a straight line. So looking at a scatter plot is important if you are calculating correlations to see if the relation is curvilinear, where it's a curve instead of a straight line. If it is curvilinear, the Pearson value will be near 0 because the curve isn't taken into consideration. And if it is curvilinear, another analysis needs to be done, either a polynomial or curvilinear regression. Looking at these scatter plots, you can see that the first in the upper left-hand corner is a strong positive linear correlation, just like we talked about earlier with the direction and strength of correlations. The second shows a moderate negative linear relation in which it's not perfect, but it's still trending in the same direction. On the bottom, you can see that there really isn't a relation here and that the data is pretty variable. And then lastly, we have a strong nonlinear relation where it increases and then decreases. If you were to run a Pearson correlation, it would see that there's no relation here, but you can see that in fact there is a trend. So this is why it's important to examine your data to find these patterns. Lastly, we need to remember that correlation does not equal causation. There could be so many other things going on here that influence these relationships. We could run into the third variable problem, where there's an uncontrolled variable responsible for the correlation. For instance, there's a positive correlation between ice cream sales and sunburns, but we know that ice cream does not cause sunburns. Rather, both are associated with increased temperature, and when the sun is out, both ice cream sales and sunburns increase. It is possible to conduct what's called a partial correlation, in which we remove or partial out the influence of a third variable from the correlation. So if you measure temperature in this case, you could add that into the statistics and hold it constant, so you are only looking at the relation between the ice cream sales and the sunburns. Regression is kind of taking a correlation a step further. The regression is a calculation, which is based on the correlation, used to predict a score on one variable based on the score from another variable. The regression equation is y hat, the hat being the little angle on top of the y, and it means that it's a predictor. It's not actually a data point, but rather something we're predicting. The equation y hat equals bx plus a, where b is the slope of the line, x is the other data points, and a is a y-intercept. You may have used the equation y equals mx plus b in other math classes. It's the same idea here, but we just use different letters. And this equation is very useful because we can plug in what x is and then predict y from it. Then we have multiple correlation, which is a correlation between one variable and a combined set of predictor variables. And this is denoted by an italicized capitalized R. If we wanted to, say, predict someone's weight, there are a lot of variables that we need to account for, including eating habits, activity habits, genetics, and so on. We could then combine all of those things into one and look at their combined effects on weight. And this is usually used as a multiple regression as opposed to just a correlation. And you don't have to do a multiple regression in this class, so don't worry about that. But it is something you might run into when looking at research and coming up with your study. So the descriptive statistics were describing what was happening. Inferential statistics allow us to take things a step further. Inferential statistics are stats designed to determine whether results based on sample data are generalizable to a population, allowing us to, well, infer things, hence the name. As you know from previous psych classes, it's really hard to obtain an entire population to study. So we take a sample. We then create a hypothesis and we collect our data. When we go to test our hypothesis, we are actually testing the null hypothesis. The null hypothesis is a hypothesis used for statistical purposes that the variables under investigation are not related in the population, and any observed effect based on sample results is due to random error. So for statistics, this means that we are hypothesizing that there isn't an effect and that anything we find is due to chance. The research hypothesis, which is sometimes called the alternative hypothesis, is the idea that variables under investigation are related in the population and that the observed effect based on sample data is true in the population. In other words, this is hypothesizing that there is an effect going on and that it's not due to chance. So taking both the null and research hypothesis together, the logic here is that we want to determine that the null is incorrect and that we are supporting the research hypothesis. And this is based on what we call statistical significance of the data. Statistical significance is the rejection of the null when an outcome has a low probability of occurrence, which is usually 0.05 or less, if in fact the null hypothesis is correct. In other words, you can think about this as the likelihood that the effect would have occurred by chance. We rely on probability, which is the likelihood of the occurrence of some event or outcome. So how likely does something have to be considered significant? Probability is denoted by the lowercase italicized p, and we examine this by setting an alpha level. In psychology, we usually set this for 0.05 or 0.01, but 0.05 is more common. The alpha level is the probability of incorrectly rejecting the null hypothesis and is used to determine whether a result is statistically significant. If our p is less than our alpha, so if p is less than 0.05, we reject the null, meaning that we support the research hypothesis. And it's important to note here that the null hypothesis isn't typically stated in the paper. You would just report on the research hypothesis for your study. We also need to be aware of the effect size, which is the magnitude of the impact of the independent variable on the dependent variable. It's the extent to which two variables are associated. Effects are measured differently depending on what test you use, but it's generally the amount of variance between two variables, and it's interpreted with different levels, so small, medium, and large effect sizes. The effect size is important to state in your paper because it helps us to understand the significance beyond the statistics. For instance, you might have statistical significance, but a small effect size, and that gives more meaning to the results. How strong and how practical your findings are depends on the effect size. Because statistics are based in probability, sometimes we're wrong and we're experiencing error in our study. Type 1 error is when we reject a true null, so we say that there is an effect when there really isn't. The chance of type 1 error is determined by the alpha level, which we talked about on the previous slide. So if our alpha is 0.05, there's a 5% chance of making a type 1 error. Type 2 error is failing to reject a null hypothesis. We are saying that there is no effect when there actually is. Type 2 error is based on beta, which is the power of your study, and we'll talk more about that at a later time. You can think of type 1 error as a fire alarm going off when there isn't actually a fire, whereas type 2 error is when no fire alarm is going off when there should be. So when we talk about choosing a sample size, how do we know how many people we need? First, we can use what is typical in the area of research. You read previous research, find what previous studies have done, and then you replicate that. But we can also be more thoughtful with how we choose our sample size by using what's called a power analysis, which determines the minimum sample size needed in a study based on the power of the study. So the power is what we talked about on the previous slide as beta, and it's the probability of correctly rejecting the null hypothesis. And there are a number of things that can influence the power in the study. One is the hypothesized difference. If we are hypothesizing that population 1 and population 2 will be very different, that's going to increase our power. If we predict a small difference, that's going to decrease our power. Population standard deviation is another one. We'll have more power if there's less variation, and also if we have a larger sample size. A lenient significance or alpha level will also increase power, so you will have more power with an alpha of 0.05 than you would with an alpha of 0.01. And then lastly, if you have a one-tailed test, you will generally have more power than if you use a two-tailed test, which splits that probability into two halves. But this one kind of depends on if the data goes in the hypothesized direction or not. So how do you know which test to run? This depends on how you set up your study and what you're hypothesizing. You can't really collect data and just figure out how to analyze it later because your data needs to match the hypothesis you set out to test. So here are some basic tests as a refresher for you. First is a z-test, which compares a sample mean to a population mean when the population standard deviation is known. There's a correlation, which describes a relationship between two variables. A single sample t-test, which compares a sample mean to a population mean when the population standard deviation is unknown. There is an independent measures t-test, which compares two sample means with a separate sample for each treatment condition. Repeated measures t-tests examine a single sample of individuals measured twice on the same dependent variable. Independent one-way analysis of variance, or ANOVA, evaluates mean differences between more than two treatments with a separate sample for each treatment condition. Repeated measures ANOVAs examine a single sample of individuals measured more than 2 times on the same dependent variable. And then lastly, there's a two-factor ANOVA, which evaluates 2 independent variables at the same time and shows the effect of each independent variable as well as a test for an interaction between the variables. Moving on, we have the chi-square test for goodness of fit, which determines how well the obtained sample proportions fit the population proportion specified. And we have the chi-square test for independence, which tests whether there's a relation between 2 categorical variables. And depending on what test you do, there's going to be assumptions that need to be met. A lot of the time, this includes normal distribution, independence of observations, homogeneity of variance, and size of expected frequencies. And if you need help to pinpoint these down or need resources on this, I'm happy to help with this. Here is a flowchart from Tessa Anderson, who you've likely taken a stats class from. She has put together this resource to help students know what tests to run based on different questions and data available. To give you an example of how to use this, let's say that you have a research question and you're interested in knowing if there is a relationship between variables, so that green box at the top of the screen. Following that, the next question would be, well, what kind of variables? If they are both nominal, you would then run a chi-square test of independence. If they are interval or ratio, you could run a correlation or a regression. So work with your group when you meet with them to figure out what kind of test you would run using this flowchart. And if you run into any roadblocks, be sure to write them down and then contact me, and we can work through it more together. So, statistics, a delight or a necessary evil? How do you feel about statistics? Do you find it fun to see the numbers in the data, or do you find it less than enjoyable? Tell me about your confidence in understanding and computing statistics. And just as a side note, you do not have to be confident in statistics to succeed in this class. I'm here to help you apply statistics to your own research, so make sure to reach out if you have any questions.